Okay, in this video, we're going to talk about how to actually test for diff. And on the syllabus, we talk a little bit about several different tests, and there's the good paper Louis Day really did 90% of the work on, where I was a co-author too. It's a good overview of a lot of different IRT topics, and I think it also is a really good overview of the different tests for diff that are out there. And if you do research on diff, you're going to run into some of these occasionally. So things like Mantel-Hansel and SIB test and PolySIB test, which is for polytomous. Those are ones that are really widely used in education where honestly a lot of the research in IRT is happening. The one that I tend to prefer and think works the best is likelihood ratio test. And the couple things I like about the likelihood ratio test, it's a well-known statistic. So likelihood ratio test exists across multiple different types of statistics and areas of research and things like that. It's a general class of statistic, just like chi-square is sort of a general measure of fit for tons of different kinds of models. You know, it's not specific to SEM or to CFA or anything like that. It's a very generalized kind of thing. Same is true with likelihood ratio test. It's a very generalized sort of class of models. So its behavior is pretty well understood. It's parametric. In other words, we know what the sampling distribution of the statistic is because it's distributed like chi-square. And so it's just well known and it's well understood and it's easily relatable across different areas of statistics for people that are familiar with this kind of test. So for example, if you were to be working beforehand with like confirmatory factor analysis, we have these type of tests there too. They're called chi-square difference tests, but they are indeed like a ratio test. And so everything sort of translates. You can explain what you're doing in IRT even to somebody who doesn't really know a lot about IRT, but is familiar with this sort of class of tests as a whole. So we're going to talk about that one in this video. And in order to do so, there's a few different kind of topics we need to cover. And the first of these is, and we haven't really talked about this explicitly, but the way item parameters are estimated. So I'm going to minimize this for a second and go to the graphs folder over to where we talked about brute force estimation of thetas. So we took our estimation of thetas. What we did is we tried out different thetas, so different levels of the parameter. Theta is a parameter, right? So it's a value that we're trying to estimate. And we tried different levels of theta, and we found the one that gave the highest likelihood using the likelihood function. And we didn't really make this explicit, but the likelihood function serves as a measure of fit for the different levels of theta. So there's a model here, and the model is essentially the formula for the item, and the item responds to the p-value and the likelihood function. And what we're doing is we're finding the parameter, the theta, that maximizes the likelihood function. And that theta is a best fit to the data. In other words, it's the theta that's most likely to have generated this pattern of responses given the item parameters, right? So hopefully that made sense with respect to theta. And we haven't gotten to it yet, and I hope we will. But the same thing happens when we talk about estimating item parameters. Item parameters essentially work the same way. You try out a bunch of different levels of the item parameters, and the one that has the highest likelihood best fits the data. In other words, it's that item parameter that's most likely to have generated that pattern of responses given theta, and so it's a very similar kind of thing there. So what we did before, we're estimating different thetas and we're treating the item parameters as known, and we're seeing which one has the best fit according to the likelihood function. But the converse works exactly the same way. If we treated theta as known, we could have and that was sort of written over here, you know, instead of the item parameters. If theta was given as known, we could try out a bunch of different item parameters that would also produce a likelihood function that looks like this. So the point of this is to say that when you are estimating item parameters, your item parameters take on the value that best fits your data, right? So you've got some pattern of observed responses. If you were to know theta, then the item parameters converge to that. They take on the value that best optimizes fit to the data and gives the best model fit, you could say. So hopefully that makes some sense. I want to go back to the slides now. So the item parameters are estimated such that they have optimal fit. In other words, item parameters take on the values that get the best fit for the overall model. And you can see that really it happens one item at a time. The nice thing about having this independence of items is that that is true for each item on its own, and then the overall model is optimized where each item is optimized, right? So we find the best item parameter for each item, and we're talking about just a single group case in this point. That leads to the best fit, and then the model fit for the overall whole test is just the sum of those fits for each of the items. And that's true for all models, and it's also true for a multi-group model. So I want to go over to now back to the graphs, and we'll look for the graphs we have on diff. If I can scroll over to that, and we'll take a look at that. So let me go to this one first. So for this case, what we've done and what would have happened to give us this graph is that we would have had some set of observed responses that we estimate, from our data, and we estimate the thetas, and we also estimate the item parameters. And to get a graph like this, what would have happened was that each group's data, was something about it was slightly different, and the item parameters, the A parameter and the B parameter for the two groups, were estimated such that they were optimized for each group. In other words, for the blue group here, the item parameter, the A and B parameters were optimized such that they best fit the empirical data for that group, right? And hopefully that's understandable, just given the analogy of what we already did with the thetas. So the way we get these item parameters, we estimate them from the data, and they take on the values that give the best possible fit to the data. The same is true for the red group. These item parameters here, we can assume to be estimated from the data to get the best possible fit to the data, and with the constraints of the model, and the model being, of course, that formula for what the p-values are, and then the likelihood formula that we looked at, earlier with data, and it's a very similar thing for item parameters. So the point here is that any of the value that we could put in for those item parameters would lead to forfeit of the model. So we normally estimate them from the data, but we could also sort of manually put some values in there, and we could measure fit just by plugging those into the model. It's a little hard to talk about this because we haven't really talked much about fit on the whole, but essentially fit is the kind of the congruence between what the model says should be the p-value and what the actual p-value is. So to kind of talk about what that looks like, again, we haven't done that much just yet, but you can kind of conceptually get your head around it. You can think about the two-parameter model here, right? This line is what we might call model implied p-values. It says this is what your probability should be given theta according to the model for these item parameters, right? That's what the model is telling us. But we could also empirically estimate this, right? If we had known thetas, we could look at the percentage of people at a theta of 0 getting the item correct, and we hope it lies on this line here, but it may not lie exactly on that line. And essentially, just like in regression, the fit of the model is how well the empirical data stick to this line that the model says it should. And that's sort of the basic notion behind what fit looks like there. Okay, so in a multi-group model, again, this happens for each group separately, right? So we estimate the model, we estimate item parameters. Item parameters take on their optimal values to give the best fit to the empirical data. So as long as you understand that, I think you're in good shape going forward to talk about how the likelihood ratio test works. Okay, so when we run a model, we actually get a measure of model fit, and it's essentially just the likelihood function that we looked at already. So before we looked at the likelihood function for different levels of data, but we also get a very similar kind of thing. It's very much analogous, called 2 times log negative 2 times log likelihood function. And so your model as a whole will have a fit associated with it, right? So across all the items, and all the item parameters, you will get a fit for the model as a whole. And again, not to worry too much about this just now, but it's really just summing up the fit of each individual item. So the point here is that when we are estimating, let's say we have two groups, a red group and a blue group, when we're estimating item parameters for the red group, we are estimating item parameters that best provide fit to the empirical data for the red group, and then we do the same for the blue group. And then if we wanted to know fit of the overall model, we could just sum up the fit of those two models and get something that looks very much like this negative twice the log likelihood right here. Okay. So what we're going to do with likelihood ratio tests is we're going to compare the fit of that model where we're estimating everything freely into two groups to fit of a model where we are making constraints that things have to be the same in the two groups. And if that difference is significant, then we can say that the two groups have significantly different item parameters. And if the fit of that joint model is not significantly worse, then we're going to say that the two groups have essentially the same item parameters. And that's how we're going to test for diff. That's sort of the basics. Okay, so what we got so far is that the item parameters estimated for a given group will take on the values that are optimal for that group to best fit the data that you see for that group. So we're going to run, and in order to do the likelihood ratio test, we're going to compare two different models. These are called, competing models. They're nested models, which we'll get to in just a minute. But the basics of this model is we're going to run one that's sort of the intuitive model, right? And so normally if we had two groups, we could estimate the model separately in each group. And by that I mean like run the two parameter model for each group, get the item parameter estimates that best fit the data for that group, and then we're done with it. And so for the augmented model or the baseline model, we're going to do that for both groups. We're going to estimate the items as though these are two completely independent data runs. We're going to get the fit for each group, and then we're just going to add the fit of those two groups together into one number, essentially. And it's called the baseline model because that's essentially what you would do if you fitted the model to the data for each group independently. And so all the parameters for like items are free to vary across groups. By like items, what I mean is item one, presuming the two groups got the same test, item one's the same for the two groups. So those are like items. Item two is the same for each group. Those are like items. But item one and two are obviously different items. You'll have different item parameters for item one versus item two in each group and across groups and things like that. So like items just means, for the same item, essentially, that both groups take. And then we're going to run a second model, and the second model is the one that's a little bit different. It's called the compact model in some literatures, also called the constrained model. And the reason it's different is because some authors and some literatures will treat the compact model like it's sort of the default model, and then they'll treat the other model, like the baseline model, like it's the augmented model, whereas other literatures will do just the opposite. So we'll go through that in just a minute here. But the other model we compare to the baseline model is a model where the item parameters are constrained to be the same for the two groups. So item one has the exact same item parameters in group one versus group two, and in group two. And obviously we know from the last discussion that when you estimate these, the data, kind of the model separately in each group, the item parameters will take on whatever value is optimal for that group. Now what we're doing is we're constraining the item parameters to be the same in the two groups. So what happens when you estimate that model is you estimate it jointly, you estimate both groups at the same time, and what you get is an item parameter that fits the data optimally in both those groups, with the constraint that it have to be the same in the two groups. So unless the two groups happen to have, just absolutely identical everything, this model is going to fit a little bit worse because the item parameters are no longer free to take on the best value possible to optimize fit for that group. It's now doing it under the constraint that it has to be the same as the fit in this other group. So you're going to get, you really can't improve fit with this model. You can only either see it be the same, or more likely it's going to get worse. And the question we're trying to answer is, how much worse does it get if these are constrained to be the same? So let's take a look at the same thing looking at a graph now. So imagine a scenario where you have this situation. So we've got two groups. We've got a red group and we've got a blue group, and I put their item parameters down here, and I've mapped everything over to their item parameters. So we're computing a p-value in the red group and a p-value in the blue group, and then we're graphing those two sets of p-values. And what we can see here, imagine this is a scenario where the item parameters are estimated separately in the two groups. So again, the blue group, the item parameters of 1 and 0 come up to best fit the data and get the optimal fit for the two parameter model for the blue group. And then same thing happens in the red group. The item parameters of 1 and 0.5 come up in order to optimally fit the data and give the best fit of the two parameter model in the red group. So in the baseline model we just talked about, we'll get exactly this. If we estimated item parameters in the baseline model, we would get these item parameters because these are the ones that best fit the data in each group, kind of when you look at them independently. What happens in the constrained model though? Well, in the constrained model, we're requiring these two numbers to be the same. The A parameter must be the same across the two groups. and these two numbers to be the same. So the B parameters also have to be the same across the two groups. And you can't really see that, I'll just do that. So what would happen in that case is you couldn't possibly get different B parameters because we would introduce this constraint that they have to be the same in the two groups. So what we would end up with is something like, around 0.25, because that's sort of right in the middle of the, right in the middle of the 0 and the 0.5 that we had. So we would introduce this constraint. So what does that mean? Well, that means this is going to fit less well for each group, because if you let the groups do what they want to, then what you end up with is a 0, right, that best fits the data in the blue group, and a 0.5 that best fits the data in the red group. When we're constraining them both to be something, to be the same, they're both going to take on a value like 0.25, and so you're going to get slight misfit in each group. So the blue group's not going to fit as well, because instead of getting to be 0, which it wants to do to provide the best fit, you're making it be the same as the red group, and it ends up being like 0.25. Same thing in the red group. Instead of being 0.5, which is what the value it wants to take on to best fit, you're going to end up with something more like 0.25. And so you're going to get misfit in both these groups when you introduce this constraint. And that misfit we were just talking about, it's going to show up right here in the likelihood function. So just like we said before, the negative twice the log likelihood, that's the fit statistic we get for the overall model. It's very closely related to the likelihood function we saw when we're looking at estimating thetas and we're estimating item parameters for the overall model. So what happens is you're going to get a fit statistic when you run the baseline model, where all these item parameters are free to vary across the two groups. And then you're going to get another fit statistic for the constrained model, where you're constraining item parameters to be the same across the two groups. And the question I'm going to answer is the misfit that we see when we introduce these constraints, is it bad enough to be statistically significant? In other words, does that misfit actually meet some kind of statistical significant criteria to say, yes, this is significant? And the statistic that you get from comparing these two models is called the likelihood ratio statistic. And I'm not going to go too much to the formula for it, but it is, like I said, part of a broader class of statistic that's used in a lot of different types of things here. And essentially what it means is you're comparing the fit of the two models, and it's the difference in those two log likelihood functions, negative two-log likelihood functions for the baseline and the constrained model is distributed as chi-square. And the degrees of freedom are the difference in the number of estimated parameters. What I mean by that is, take a case where the model was allowed to be independent across the group. So the baseline model, we're estimating different item parameters for the two groups. And for a single item, you can see we're estimating 1A and 1B parameter per group. So that's four total parameters being estimated. So I'm just going to write that over here. And in the case of a constrained model, if we constrain both the A and the B parameters, then we're going to end up with an estimate that is essentially somewhere, it's not going to be exactly the average, but it's going to be pretty close to the middle of these two parameters for the two groups. And so we're only going to have then two unique parameters in the constrained model. So the difference between the two is going to be just 2. It's going to be just the difference in the number of kind of estimated parameters in the kind of the baseline model minus the number of estimated parameters in the baseline model, and this is going to be your degrees of freedom. So in this case, since there's 2 item parameters per item, you're going to have 2 degrees of freedom per item. So if we had 10 items, we would have a degrees of freedom of 20. So what you would do is you would go over there and look at that negative log likelihood for the baseline model, and then you would look at the negative 2 times log likelihood for the constrained model, and you would take the difference in those two and you would evaluate it as a chi-square where the degrees of freedom is this number, wouldn't it be 20 in that case, right? It would be the number of parameters that you're estimating per item times the number of items. So if it were 10 items, it'd be 20. Okay, the reason we can do this is because these two models are nested. And nested models, again, it's not unique to IRT. You can also see this in multi-group CFA and other kinds of places. And models are nested when you can take one model and introduce a constraint to get a different model. So in other words, the models, one model is a special case of another model, right? So probably the most basic example we've seen of this in this course is the Roche model. The Roche model is essentially a special case of the 2 and 3 PL models. So we can take for example, the 2 PL model, And we can set all the A parameters to a set value, and that will be equivalent to the Rush model. And so the Rush model is nested within the 2PL. So we could compare the fit of the 2PL and the fit of the Rush model and determine empirically which model best fits the data. We talked about a little bit when we talked about the generalized graded response model and the graded response model, I think it was, or no, wait, it was generalized partial credit model and the partial credit model. How the partial credit model is a specialized case of where you're just introducing constraints on the generalized partial credit model. So anytime you have nested models like that, you can evaluate the difference in fit empirically using a chi-square statistic through this likelihood ratio test. So there are a few different issues that come up when you're doing this. The first one is something we've already addressed a little bit. We talked about polytomous data, and this really comes up mostly in polytomous, is that you have enough response categories to estimate the V parameters. If not, you need to collapse those categories, again, for polytomous data prior to doing any kind of analyses in R. The other big question is what to free and constrain, and different authors have taken different approaches at this. Some authors have considered the kind of the constrained model to be the baseline model and have compared it against what they call an augmented model, where they then free up item parameters for one or more items. And also you can choose which item parameters to free. Other people have taken kind of the opposite approach, where the baseline model, where everything is free, is considered sort of the baseline, and then you compare it to a constrained model. So there's a lot of questions, and the one we just looked at, I kind of gave you an example where simultaneously we were constraining both the A and B parameters, but you don't have to do it that way. You can constrain just the A parameters to be the same and let the B still be free across groups. And you can evaluate that, again, using likelihood ratio test, where the degrees of freedom is going to be equal to essentially the number of items, right? Because you're estimating one different number of parameters instead of two A parameters, just one A parameter, one different per item, and then you just multiply that times the number of items. You can do just the B parameters, you can do both simultaneously. And in the graded response model, you can even do just some of the B parameters. You can do like the B3 parameter if you want to. Now, I don't think I've ever seen anybody do that. It doesn't really make much sense to do that. I don't know why you would do that. But you can certainly look at just the Bs or just the As, and people do sometimes do that. Um, that is actually relatively common when people do kind of confirmatory factor analysis tests. There's a long literature there that's totally independent from the IRT literature, where people would kind of evaluate these things separately, and some of the IRT people have done something similar. So it really depends on what you're doing. If you have a hypothesis that A parameters differ, you evaluate that hypothesis and let the Bs vary still. You could do the same for just the Bs, or you can do them both simultaneously.